Vector potential, yeah, that's it. And position, so it's pretty happy. Now we can, we gotta pick a gauge now, so let's just, for fun, pick the Landau gauge. Or we can do it because Stone Cold said so. And if you recall, that's the gauge we just used to solve before. So this gauge leads to a new Hamiltonian. Well, not a new Hamiltonian, but a gauge transformed Hamiltonian. So that's, we plugged in our vector potential, and that's what we end up with. Happy Dojo. This actually equals. Okay, so as you can see, this is kind of nasty, and pretty soon is where I'm going to take this nasty step too. So we can choose H and PZ to be simultaneous eigenvalue or eigenstates with eigenvalue 0. That's technically because H and momentum in the z direction commute. So then our Hamiltonian will take a different form a little bit. Okay. So after redefining that, and that also takes into consideration the fact that that we take the eigenvalues of p sub y to equal hk, or h bar k. So now we kind of notice that this is just a phase-shifted harmonic oscillator like before, even though you don't really notice it right here because there's all this crap. But we'll notice it when I put it into the next form. That is what took 2 chalkboards full of algebra. I mean, it had to be bad if it took me and Albert 2 hours. It'd be horrible. Okay. I feel like there should be music when this is going on.
I was thinking you should have sexy girls in bikinis writing the equations for you already.
Yeah.
You really like women. The textbook talks about it too.
Yes, it does.
We have something in common. That's good.
So now this is in more of harmonic oscillatory form. Oh, there's no squares here. Wait, yeah, there is. Anyways, this is our omega. Oh no, there is no squares there. Okay, so yeah. Anyways, this is the harmonic oscillator form. You can see it's phase shifted by this crap, and then you got this crap added onto it. But for the most part, it's